So this is going to be live demo, and we'll see how it goes. Okay, so Alex asked me to talk about, how to like kind of look at Legion profiles. And so what I want to do is actually show some Legion profiles and talk about what I look for when I look at Legion profiles, so everyone can kind of look at how you might read one of these things. So to launch Legion profile, you literally just type Legion prof, and then you type the command you want to do, right? And so I'm going to use the view command here to just launch, and then, open up a whole bunch of log files that you pass in. They're generated by Legion prof, and so these were generated, in advance. So I'm not actually running simulations here, but Legion prof is loading, our simulation here. And before we actually look at this, I'll actually take a moment just to look at this this output here, just to explain to people what this means. So Elliot mentioned in his talk that there's some timing skew. So we actually have detection now. Effectively, if you're running a distributed system, it's actually really hard to synchronize clocks between different nodes. And so Realm does its very best to make sure that the clocks are aligned between the processes. Like the timers start all at the same time on each of the nodes. But sometimes there's a little skew. And so Legion prof actually will use the messages that it's profiled between different nodes to look for this timing skew and see how bad it is. And you can see some of these, effectively are computing averages for how much skew it seems between these different nodes. Like some of the nodes will appear to have started, have their timing be just a little. Effectively, when you get a message that looks like it arrived on a node before it was sent on another node, that's a sign of skew, right? And and Legion prof will actually check that. I think for most part you can ignore these as long as they're in the range of about. Nope, Stanford is complaining about the network. Okay, well let's just turn off the Wi-Fi here just to avoid. I don't actually need Wi-Fi for this. So Legion prof is just complaining about this. These are averages, and as long as they're small, maybe about 100 microseconds, you can probably just mostly ignore them. There's a few bigger ones in here, some 600 microseconds ones. This doesn't actually mean that your profile is bad. What it means is that you can't necessarily compare the position of boxes on different nodes, right? Because effectively they might be shifted in the order that they actually ran in, right? So, but looking at the profile that we're going to look at today, and for most of your profiles that you generate, this timing skew is mostly irrelevant. Now, if you start to see timing skews that are like a millisecond, you should really start to pay attention, right? That means that relative positions of boxes could be shifted by quite a lot. And we've actually seen cases where it's 10 or 100 milliseconds, right, in some machines, right? And that's really off. And then that'll be really confusing when you look at those profiles, because effectively Legion prof will align all of the nodes at point 0 over here, right, at the left side of the thing. But really what's happened is some of the nodes will be shifted relative to each other. So, watch out for timing skew. But for the most part, this is just informational. It'll say that there's warnings that it found timing, if it did find timing skew. But I think most of the things, I should probably make this warning a little bit less conspicuous these days. But yeah, it's something to be aware of, and it's just informational mostly for folks that are reading profiles. Okay, so when I look at a Legion profile, right, so I've actually got, let me actually scroll up to the top here. This is our Legion prof interface. Hopefully everybody has seen this. So I'll give a brief overview of this. So the very first thing you'll notice is that these first set of lines here, this all category, I actually think it's really useful to see this, and we render this intentionally, right? Because I think what this provides is a summary of the utilization, for different kinds of processors, your GPU processors, your CPUs, your utility processors, your system memory, how much memory you're using, right? Effectively, it gives you sort of an overview of what all the nodes are doing, right, inside this profile. And you can actually learn a lot from this, right? Our human visual systems are really acute at picking up patterns and stuff in these kinds of things, right? And so, this particular simulation, it's really kind of obvious when the simulation actually starts. It's right about here, right? When we start actually running time steps and you start getting duty cycles on the GPU, right? And that's when the simulation actually started. Everything before this is just sort of startup and getting things running, right? In fact, you can see there's the CPU is very busy here running probably top level tasks to start things up and things here. And so you can kind of look for the phases of your application. You always want to make sure you're aligning on the phases of the application that you're actually simulating. Make sure you're looking at the right part of the profile, because not all parts of the profile are necessarily interesting. And you can see nice cycles on your utility processors here. You can actually see the duty cycle here much more clearly in aggregate across all the nodes than maybe what you might see on any individual one node, right? One node might be kind of spiky, but here you can kind of see the pattern kind of aligning with the actual execution here. So, try to orient yourself in your profiles and try to actually look at those things. So if we actually look at, obviously Legion prof lets you zoom in often when I want to look at like, what's going on with performance or something, don't start at the beginning. Like the beginning is almost never representative of what's actually interesting. It's always better to start somewhere in the middle. Just pick a random range of time to kind of zoom into to take a look at, what's actually going on here, right? And I often like to look at these duty cycles, like, and I call these duty cycles, that comes from like electrical engineering background, like, you look at how much your waveform diagram is going up and down and stuff, right? And you want to look at how busy like your GPU and stuff are, right, relative to how busy your utility processes are, relative to how busy your CPUs are, and also relative to how busy these like the channel is down here for actually moving data. So right, channels are for actually doing the copies for moving data between different, memories in your side of your machine and stuff like that, right? So it's often really good to look at your GPU utilization, but then also like looking for like when there's gaps in here, you often want to look for the thing that's actually like causing this gap to actually like be here, right? Why was my GPU not actually running here? One thing that's actually often useful to do is like sort of align your sort of cursor here, right, on top of one of these gaps and try to understand what's going on. You look for something else inside the machine that actually is running at that point in time. So if I scroll down here, let's see if I can find something interesting that's actually running. Yeah, so you can actually see like, this node was actually busy doing something in the utility processors at that same time. And it's often not an accident, right? Things that are, often when you see a gap in one place, it's because something else is happening somewhere else. Now we actually have some stuff that actually makes this a little more explicit now. And Elliot called it out, and I actually want to show you a little demo of it here. So let me actually expand one of these lines here. Right, and I'm going to zoom in here a little bit more to make this a little easier to see. Let's see. So when you get a gap like this, right? You think the light mode would be easier? Let's switch to the light mode. Is that better for you, easier for people to see? Okay, yeah. That's good to know. All right, good user interface tip. So yeah, we'll do a little digression here. Yeah, you have light and dark mode. You also have controls down here, which is very interesting. Yeah, so. Yep, you can always adjust those things. Yep. Okay. All right, so what do we actually see what's going on here? We do have this gap on our GPU here, right? And we actually want to understand what's going on here a little bit more, right? And so one thing that you can do is you can actually find like one of the first things that was last to start, right? Or what we want to know, like, sort of what was the thing that prevented this thing from starting actually earlier, right? And this is the critical path functionality that we've added. Right, so I can click on this GPU kernel, right? It pops up a little box here, right? And this actually says, it tells you like when this kernel started on the GPU and so forth, and how long it was running for, and everything. One of the nice things it shows you is who called this kernel, right? So we have this caller functionality that says, this is the task effectively that called this GPU kernel, right? You can actually click pan to item here. And it says it will be, this is one of the tricky things, and I've complained to Elliot about this. Is he actually here? He's not here, so I can complain about it more for you guys. And that is that oftentimes, like the thing that's actually trying to be rendered is inside of one of these little gray boxes here, right? It says item will be displayed once available. You might need to zoom in to actually see this thing, right? So you see I zoomed in a little bit, right? And actually, like, then it popped up the box for me, right? I wish it would actually, and I think it's one of those things, like if you change this show controls down here to change from pan to zoom, it'll actually zoom in and like find that box. But I don't actually like the zoom feature because it like always over zooms and makes that box that you're zooming to be the full thing. But it does do that, and so I like to use the pan, and then I sort of manually zoom as I need to get to where I need to go. Right. And so now we've got this is the task that created that kernel, and this is the critical path functionality that we were talking about. Is that all tasks and actually everything in Legion Prof now is annotated with critical path, which says what was the last thing that had to happen that prevented this task from starting earlier, from running any earlier, right? And then what this is saying is that effectively the reason this task didn't start any earlier was that it hadn't been created yet, right? And what it's saying is that, and I can actually, let me expand the utility processor here, but effectively it'll give you a pointer to the thing that actually called this task, right? In this case, it was this replay physical trace task. And if I scroll up right here, you see we're still right here. And so this replay trace task is actually kind of late in running, right? It actually didn't even start, until right before things actually needed to start executing. Now, usually Legion is running ahead, in this particular case, this application pennant actually suffers from sort of a blocking behavior where it has to synchronize to test a condition, a convergence condition, every iteration of the loop right now. And so it's often hard for the runtime to get ahead. In this case, the replay trace should have, it actually should be a little bit further ahead, and we'll look at like one of the anomalies that's causing that. But effectively, you can find the thing that was effectively the last thing that was preventing this thing from starting earlier. We're going to look at these anomalies just a little bit more later. But you have this functionality. Let me actually zoom out here a little bit and see if we can find one that has a different sort of precondition. I'm going to zoom over here. Let's find one of these tasks over here. So by the way, I'm looking at this GPU host, right? That shows where the tasks are actually running on like a host thread that's bound to like a CUDA context, right? And this GPU dev channel is actually showing like the kernels that actually run on the device, just that distinction is clear here. Right, and here's an example of a different sort of critical path, right? Instead of like, something not starting earlier because it wasn't created soon enough, right? In this case, what it's saying is that this task didn't start earlier because this other task, was still running. Let me actually zoom in here to expand it. There we go. Right, and you can actually see like, it'll give you a pointer and then pop up the task that started right before it, right? And so you can actually find, with the critical path stuff, sort of, it's the most common question when you're looking at profiling. It's like, why didn't this thing start earlier, right? And now there's an answer for that for every single thing in Legion. I actually don't know of another profiler that actually has that functionality. And this is actually true of all sorts of things, as well, including copies and instances and stuff, as we'll see a little bit later. So you can actually find sort of what's taking a long time and find where there's sort of a critical path through your code that is actually like causing a delay and something starting sooner than you think it should. Let me zoom out here a little bit. Take a step back here. So this particular application, I would say this application is running okay. It's not great. There's gaps on the GPU, right, which we clearly don't like. And it turns out it's because this analysis, or sort of the utility processor is getting busy. You can see like here's an example of a case where like the utility processor is busy, waiting for stuff to happen, and that's causing delays in when things actually run. Now you see the utility processor isn't like inherently, it is actually inherently busy, and this is actually one of the mysteries that that Elliot and I were looking at these profiles last night because he generated these on sapling, and we're not entirely sure why this is happening, but some of the mapper calls are actually taking a very long time, right? And so Legion actually profiles all your mapper calls and stuff, and you can see that this application is spending a very long time in some of these mapper calls, right? Like it's taking what is that? Running for about 7 milliseconds, right? Inside of your mapper there, right? Just in this little range right here. So the profile is a little strange here is that like this is a whole mapper call, and you can see sort of the running times of the darker oranges and the waiting times of the later ones, right? But if I click on one of these ranges, right, it was actually running for like 12 milliseconds here. It took like 53 milliseconds to handle this whole mapper call, which is very unusual, and we're not entirely sure yet why that is happening. So that's clearly causing the delay, and you can clearly find out exactly why this particular oh, that was not what I wanted to do. I wanted to do this one, right? That sort of very busy utility processor stuff here in the mapper is what's causing this gap in here, right? For between things running, right? There's sort of some analysis happening, right? And the tricky thing will be you'll have to go kind of look at your map. This is one thing Legion Prof doesn't tell you like why your mapper took that long, right? You actually have to kind of profile that yourself and go look at your mapper call and understand a little bit better what's going on, but. I kind of like to look for gaps and try to understand what was the previous thing that happened and then also what was running at the same time, right? And try to understand what's going on there. If people have questions and stuff, please stop me and ask questions or want to understand more what's going on here. Okay, so let's actually look at maybe another anomaly that we saw that sort of a different kind of like failure mode that you might be able to diagnose with Legion Prof. Let's go back here. So actually I already looked at one with the mapper anomaly. Let's take a look at the anomaly copy. Okay. A little bit simpler profile to look at. Okay, so if you look at this one, you can see we have a different pattern here for what's going wrong with our application, why it might be slow, right? You can see our GPU utilization is still not great here, right? It's not busy all the time. But the cause is going to be quite different in this case, right? We can actually see that the problem here is actually with data movement, right? And that's because this channel utilization is really high, right? Bordering on like, like oftentimes 100% of channel utilization, meaning we're moving lots and lots and lots of data, right? And so if we zoom in over here, let's actually expand some of these things. Like you can actually see, our GPU utilization is actually pretty sparse, right? The kernels actually running the device aren't taking a lot of time. Right, and that's because if we expand this channel down here to look at all the DMAs and stuff like that, right, we can see there are lots of copies that are taking a long time. In particular, you have to, there's a little syntax that we use here for annotating the names of these memories. So what this, the way you read this is node 0 system 0 to node 0 frame buffer 2, right? Node 0 system 0 to node 0 frame buffer 3. Right, and you can see if you hover over it, it'll actually expand that for you so you can actually understand what the little annotation means. But if you don't want to do that all the time, there's a little shorthand that we use for naming all the memories and stuff. Right, and so what this is telling me is that there's lots of copies from the system memory down to the frame buffer memory. And they are taking a long time. And that's like 80 milliseconds for in this particular case, or 174 milliseconds in that case. Right, and that's because they're copying over the PCI bus, and it's really slow, right? And I mentioned I promised you to tell you that everything has a critical path. You can see that even copies and stuff have critical paths now, saying what happened right, that happened to prevent this thing from starting earlier, right? And so all these things have critical path annotations, right? And one thing I should mention here is I try to give you little hints with these colors here about things that are going wrong that you should probably pay attention to. And this one is red because effectively what this is saying. So I should mention what all these different little things here mean. So let me describe what deferred and delayed is, and then I'll say why deferred is actually annotated in red. So deferred is how long your copy spent from the point that it was launched by like the Legion dependence analysis to the point where its event precondition was triggered, okay? Now, in general, you'd actually like that to be pretty long, right? That means that the runtime is running ahead, building up the realm event graph in advance of like when your execution is actually taking place. So like, it's not bad to see and in fact, that's what this little red thing is saying, is that this is actually very short. We actually want this number to be much higher. We'd want it to be at least like in the tens of milliseconds or so, if not hundreds of milliseconds, right? If Legion is running ahead, building up the realm event graph, this deferred value should actually be fairly large. It should be like tens or hundreds of milliseconds. And when it gets like less than like a millisecond down to like a few hundreds of microseconds or less, that's where the execution is catching up with Legion's dependence analysis and starting to cause bubbles in your pipeline and latency, right? If it ever catches up entirely, well then we're exposing latency and stuff, which is not so good, right? And so we sort of mark these as red, sort of indicate to you we're not far enough ahead. Legion is not running far enough ahead in this particular case. Now delayed is actually saying something different. So delayed is actually saying, once the event precondition for running this copy triggered, how long did it take before Realm actually started executing it, right? And you want this number to be small, right? In this case, it's actually nice and small. It's like 2 microseconds, right? So like, the Realm background worker threads picked up that copy right away and started running it, almost instantaneously, as soon as the precondition event triggered, right? And so you can actually understand like how long, where your tasks are and how long they waited for their events to trigger, and then also like how long it took them to run, right? And so very long values of delayed, like so for example, if you had lots of tasks that were ready to run on your processor and it's taking a long time to get to one of them, right? You'll actually see a very big value for delayed because it was waiting for, it had its precondition event triggered, but it might have to wait a long time to actually run, and then we'll mark that more yellow or red depending on how long it has to wait for. We do try to color some of these things to try and give you some hints as to what's actually going on. Let's see. I wonder if I can look at some examples here and see here. So yeah, so here's another example, one of these red things. So you can see here's an example of deferred that actually looks pretty good, right? Legion was actually like 188 milliseconds, ahead launching this thing, right? And then it didn't have to wait too long to be picked up 59 microseconds. What this triggering latency says is like, how long did it take for Realm to get around to triggering, the post-condition event. Is it post-condition or precondition? Let me remind myself. I think it might actually be the, let's see, yeah, it's actually the post-condition. It's like from when the point where the task finishes running to the point where we actually trigger the event and actually shows up downstream of that, like how long did it actually take for that task to actually finish, like triggering its event. So this is a sign that like Realm might be a little bit overloaded if you actually see triggering latencies that actually start to get into the large ranges. Let's see here. So yeah, so in this particular case, as I said, the problem here is with these copies, right? And effectively what's happening here is we're actually doing copies back and forth between the host and the frame buffer memory, which suggests that you probably shouldn't be doing that, right? Like it would be good if all of your data was staying on the GPU. In this particular case, there's like a bug in the mapper that is placing its instances in the wrong place. You can actually see which instances you're using here. So let's see. Actually, why is this not showing the instances? Don't copies show which instances that they actually use? Like, what's that? Oh, yes. So yeah, here's the okay, yeah, you're right. Yeah, so source and destination are your instances. We should probably name those a little, as Seshu, I think, requested yesterday. But you can actually pan to these items, see which instances they are, and what made them, right? So the creator here is actually the thing that made them. So you can see this is actually made by a finder create call. We can actually pan to that item, right? And where did it pop up? Oh, it'll be displayed once I zoom in enough. Let me actually switch to the zoom mode and we'll see how well that works. We'll switch to zoom and we'll click on this and see how it works. There it is, right? And you can see that this was a map task call for 58, which is probably going to be an index-based launch, which is why it doesn't have an equivalent. There it is for initialized topology, right? So you can actually find the thing that actually made this instance, and then you can go look at the corresponding mapper call that you invoked for mapping this particular task initialized topology, and say, why did I make this instance in this particular memory, right? And then also downstream you can look at like why did I pick to use this instance as part of the copies and so forth, and so you can go through and look at like why things are happening. So you kind of learn the relationship of these different things. You can figure out how to work backwards to figure out why something bad is actually happening. So let's see, what else is worth talking about? I'll also point out here while I'm here, everything has a critical path, including instances. So instances actually have critical paths too, looking at sort of what prevented them from being allocated even earlier, right? So it's the first thing that uses an instance has to wait for that instance to be created, especially with Realm's deferred allocation stuff. And so even instances have critical paths. And this one is yellow. I should probably use a slightly darker yellow color here. But what it's saying, let's see if I highlight it. Can I highlight it? Nope, can't highlight it. It'd be nice if we could highlight and copy stuff.
It's blocked on an eGUI update, which breaks something else.
Okay, blocked on an eGUI update that updates something else. Okay, all right. Yeah, so effectively what's saying is it's waiting for another instance to be deallocated in order to allocate this instance. And that's causing a little bit of delay in the creation of that particular instance. But it's not, Legion Prof couldn't quite prove it's on the critical path, so it just marked it yellow, I think, instead of red. But yeah, so it tries to give some guidance as to what's going on there. Okay, let's see. Other things that are worth looking at. I know some of you have seen these these number of hops parameters. This is often a good thing to look at for copies that are really slow. So if your copy is slow, oftentimes it's because it's a multi-hop copy. And we say anything that has more than one hop is a multi-hop copy, quote unquote. So if you hear us use the term multi-hop copy, that's what we mean. It'll say more than one hop in this particular box here. What that means is that Realm is having to move the data more than one time between two memories, right? Often, this happens between multi-node runs, or if you're moving from like a pinned buffer or from a memory that's not pinned into a pinned memory such that it can be like RDMA'd or something like that, often will cause a multi-hop copy. We've sort of been trying to explore ways of like actually annotating, what the path is that, where the hops are. So you can actually visualize that a little bit better or understand a little bit more what's going on. But often you'll see like, if there's a multi-hop copy, that's one thing to to look for in slow copies, and then you can ask yourself why it's multi-hop and whether there's a mapping that might allow you to get a single hop copy, like putting it in a memory that's this particular instance in memory that's more directly accessible via other nodes and stuff like that. Yeah.
Could we possibly get bandwidth numbers for copies too?
I think we could. So you can kind of compute effective bandwidth numbers, right? We could add that in, right? The thing that's a little strange is that, like, if your copy is sparse, like if the index space of the copy that you're doing is sparse, then you're probably not going to hit full bandwidth, right? But we can compute effective bandwidth and add that in there. That's really easy computation to do for the profiler. Yeah.
And then I was going to ask if we could get like a red thing
When the bandwidth is
below the expected bandwidth.
below the expected bandwidth. I think we could do that because I think we have that information from the Realm machine model, so we know what the expected bandwidth is for accessing.
Well, if it's a multi-hop copy.
It's a multi-hop. Well, then you have to pick like sort of like what is the bandwidth of the least memory along the path, right? And like and kind of like figure out how far off you are of the effective bandwidth that you should have accomplished, right?
That would actually really help in kind of identifying
Yeah.
when you have interference.
Right. Yes. That and we're almost certainly getting interference in this case because I think let me close some of these boxes. This is one of the other annoying things about the profilers, like how do you deal with all these little boxes? Let me actually reset here and let's actually close this and I'll zoom in down here. But yeah, there's definitely multiple copies going on at the same time here, right? And so, I guess there's another pattern to call out here. Like if you look at one of these stacks here, so one thing that is a little fuzzy about how Realm renders or reports profiling for copies is that it makes it look like all these copies are running concurrently. That's probably not what actually happens, right? Like Realm will sort of record the starting time for a copy, like as soon as like its event precondition triggers and it goes into the queue. What's really happening here is that Realm is kind of running these things in order. So probably this copy was actually running first, and then it finished, and then this copy probably didn't actually start until here, and it ran to there, right? And then this one starts here, and it runs from there to there, and then this one starts here and runs from there to there, all right? And it's kind of hard to show that. We don't actually have waiting data per se for copies the same way we do for tasks, right? For tasks, we don't see this sort of like pattern, right? Because we'll actually record when we're waiting on events and stuff like that inside of tasks, and you'll see the blocking behavior. That's true. Like in this particular case, yeah. So these copies, hopefully these copies are offloaded to the GPU's DMA engine for doing it, and they're run in parallel with the kernels. But yeah, if Realm is launching a kernel here, we would like to kind of know about that because then it's going to interfere with kernels that might be running up here, right? And like might be delayed because of that too. So I think we're kind of trying to push Realm to get some more detailed profiling information. This is like the kind of stuff that we might want to know in a little bit more detail. So.
The new copy feature that I pushed that apparently is broken based on you should be able to get to the GPU kernel stuff.
Yep. Yeah, we can file bugs with it. Yeah, to try and like determine when the copies are launching kernels and stuff like that. Yeah, so we could render that too. Yeah, which GPU it ran on and for how long. Yeah. Okay. Let's see. Some other things that are worth calling out while I'm here. So one of the other things that Elliot mentioned that we actually track now is when you wait on an event now, every one of these will generate a backtrace for you and actually tell you where you're waiting. So like effectively you can see this like a backtrace. Oh, if I another thing, like if I move my mouse off the box and onto the pop-up box to like look to point at something, it doesn't. Okay, fair enough. There you go. Okay. All right, so we've actually got like a backtrace here showing where we're waiting. It doesn't render particularly nicely, but it is here, right? And so this will actually tell you where you're waiting, right? And so you can see the top level task here is waiting in a future get result, most likely the future at the end of the computation, right? And that's where it's actually blocked. So everything that everywhere that we block now, we record the backtrace for we're waiting, and you can see how long you're waiting for and stuff, and how long it took for how long you're actually waiting for, and yeah. And you can actually see what woke you up, by the way. Like, so even waits have critical paths, right? And I'll show you like, the thing that actually woke this thing up was a trigger task mapping that triggered, an event that, actually woke up the waiting thing when it actually was ready. Sorry, I was pointing at the wrong thing. The critical path is here. Use your event triggered by a trigger commit. Sorry. I pointed at the wrong thing. But anyway, that's there for you to take a look at as well. Okay. Let's see. I think that's most of my demo because we looked at all the anomalies that I think we saw. I think it does show a little bit about, there's Jonathan's meeting. So I think this does show, sort of what Legion Prof does and sort of how to read a profile, some of the things that I look for. There's still some things that are missing in here. So for example, like we don't see Realm background worker threads. We don't see CUDA driver threads, right? Things that can cause interference that we don't necessarily have visibility to in Legion Prof. And that's still sort of a source of like, confusion. It's like, well, if you can't see it, then you can't understand it, right? And I actually suspect that some of these, I was telling Elliot, some of the sort of bubbles that we were seeing, in those long mapper calls, I actually suspect are CUDA driver threads and the OS scheduler sort of time multiplexing stuff with those driver threads and causing tasks to look like they're running when they're really not. They've really been descheduled by the OS and we can't actually see it. So there's limitations to what we can see here, but at least we can see lots of Legion stuff, which is very interesting. So what questions can I answer for people? Like, are there parts of the profiler that we can look at right here that I can explain something about how it works that might make things easier for folks to understand?
I have a quick question. So that one thing where you weren't quite sure why it was getting delayed in the first profile.
In the first profile, yeah.
Yeah, the big gap.
Mm-hmm.
The gap that was bigger than the rest.
Yeah.
This gives me deja vu. I feel like we've looked at this kind of thing before, where all of a sudden everything is slow. And it's kind of clear, why. We always suspect the operating system has decided to, take a break or something, or pull your program, take a break.
Yes, I'm not entirely sure. I mean, we definitely have seen stuff like that before. I can pop it back up here. We can find a nice, if I zoom in enough here. Yeah, here's the one. Here's a good example of it. Right, like the select task mapper call that ran for 22 milliseconds right there, right? Like, now, so there is a way to actually get to the bottom of this, and this is actually more information than we had before, right? Like, if you have like a vtunes profiler, Ron, we're using Magic Trace, right? And you could actually like generate one of those profiles in parallel with this, right? You could actually line them up in time and find this exact, sort of point in execution in this thread, and like, actually see what was happening, right? And see whether it was like actually running or whether it was descheduled. So does Magic Trace show you if like the thread is descheduled by the OS, or like what does it show you?
Well, it shows you all the stacks. I guess depending on the permissions you have on the machine, you might be able to see what the kernel is actually doing.
Mm-hmm.
I didn't see anything specific other than the profiles I was looking at, but you probably can see something.
Yeah.
You can see way more detail.
Right.
You can see all the function calls.
Right, because this is the thing to remember about Legion Prof is it's not a sampling-based profiler, right? Like it's effectively just measuring start and end times at specific points in the program. And if our thread is descheduled, we don't know that, right? We just know that it took this long by the system clock time to get from point A to point B, right? And we don't know what happened in the middle, whether that thread was actively running that whole time or whether it was just like, it got descheduled by the OS or whatever, right? And so we're not actually doing sampling. And so if you have a complementary sampling-based profiler, that'll be much higher fidelity, also more expensive, right? And with much less like semantic information, but much more accurate sort of like actual what happened execution-wise on the hardware. There is a way to do it, and it involves like either doing an Insight, like an NVIDIA Insight profile or a Magic Trace profile or a vtunes profile at the same time, and like aligning them and figuring stuff out. And I don't have a better way of doing that right now, but that is a way to do it at least. So there's a way to answer that question. Yeah.
What questions are there? This is like the most common question. Like how do I debug my profile? So I thought we should spend a few minutes on
Yeah, so like, are there questions other folks have about, as Alex put, how do I debug my profile? Like, are there other patterns that you've seen that you don't understand, or things that are confusing about the profiler interface that don't make sense?
Would it help? Do you have a profile or one that is just read
Yeah, so I actually do have one of those. I do have, actually, that's a good point. I do have one that's like runtime limited where I actually ran like a really tiny problem size. And you can just see that like nothing is happening on the compute processors, and the utility processors are just busy all the time. Here's a good example of like this example of a runtime limited profile, right? And so what you see is this, just the utility processor is super busy across, you know, all the nodes in different points of time and stuff like that. And this is a CPU only run, so there's no GPUs here, but your CPU utilization is really, really low. So if you see your utility processor busy like this all the time doing analysis, this was without tracing, I think, yeah. There's no tracing in here. There's lots of like, you know, actual physical analysis and stuff like that. This is a runtime limited application, right? Where Legion's runtime analysis is literally dominating the execution time, which means your tasks are not big enough to actually, you know, accurately or to fully like amortize the cost of Legion's dependence analysis and stuff. And so one thing to keep in mind here is like, you know, the Legion profiler interface always scales these things to, you know, the full run. Right, in this case, this run was actually incredibly short. It was only like 5 seconds for the whole run of everything, right? Whereas some of the other profiles that we were looking at before were like tens of seconds, right? And so, you know, when you shift from one profile to the next, just keep in mind that like there are scales there, right? And so it doesn't mean that this profile was the same length as the other time. It's not like we have an absolute time value scale there. So, but this is what a runtime limited profile looks like. Just lots of utility processor work all the time, and not much happening on your CPUs. You know, I guess that's the top level task there. In fact, you can't even really see the application tasks. They're so tiny. You have to like zoom in on some of these things in here to actually find the real application tasks. There's an advec position half, a tiny little application task. And you see, you know, the critical path again is dependent on user event trigger by, you know, something on the meta processor. So, or on one of the utility processors, one of the meta tasks. So, yeah. Other questions? All right, I hope you guys try out the profiler. Elliot and I put a lot of work into it to make it do lots of cool things, I think. Like the critical path profiling, I think, is like just especially novel. There's no other profiler I've seen that has anything even remotely like that. So, yeah.
All right, everyone.